multi-agent systems as Continua that was directed under great advising of my beloved advisor, Professor Suhada Jayasuriya. So for my PhD, I developed algorithm for motion control of multi-agent systems based on principles of continuum mechanics. First, the question arises that what is a continuum? To have a good view of a continuum, assume a portion of water that can form the shape of the container that surrounds water. So, and also a portion of water can freely deform and move on the floor. So the nice thing about continuum deformation or deformation of the water is that no two particles of the continuum or water that were initially separated occupy the same position during deformation. So it is a very interesting feature that can address the problem of interagent collision in multi-robot systems if robo-agents or robots of a multi-robot system treats as particles of a continuum where deformation of the continuum prescribe evolution of the multi-robot systems. So formation control of multi-robot systems have many applications, such as formation flight, air traffic control, transportation engineering, gaming, and environmental sampling. For example, environmental sampling can include mission in hazardous environment that may be dangerous for human health. So by applying a multi-robot system, we can do a specific task in a hazardous environment. So to apply continuum mechanics principles for evolution of a multi-robot system, we propose this simple approach. Assume that we have a number of robots and they are supposed to move on a planar field. So we place three robots, robots 1, robots 2, and robots 3 at the vertices of a triangle that is called leading triangle. These three robots are leader robots, meaning that these three robots move independently and choose the paths that the entire multi-robot system needs to select. We distribute the rest of the robots inside the leading triangle, and they are follower robots. So at the second step, we determine some parameters, alpha I1, alpha I2, and alpha I3, based on initial position of a follower I and initial positions of the three leader robots by this simple relationship, but I don't want you to delve with mathematics, and I want you still enjoy your lunch. So I go to the next slide. So then, now followers know the parameters alpha I1, alpha I2, and alpha I3 based on initial positions, its own initial positions and initial positions of the leaders. Then leaders choose the paths in such a way that they don't collide with obstacles. So a schematic of path planning for multi-robot system is shown in this figure. Then we let each follower to update its own position by alpha I1 R1 plus alpha I2 R2 plus alpha I3 R3. R1, R2, and R3 are the positions of the leaders in a finite horizon of time that are informed to the followers, and alpha I1, alpha I2, and alpha I3 are the parameters that followers obtain based on initial positions. So if we do that, we can treat evolution of multi-agent systems as a continuum deformation. This is an example of guiding a multi-agent system inside a narrow channel that deforms as a continuum. So I run it again. So you see here every follower agent knows positions of the leader agents. Now the question is that how the desired continuum deformation can be learned by the followers if followers do not directly access to the leader's positions and they just access to the positions of some followers in the vicinity. So we propose a communication topology for this problem and suggest that first place leader agents at the vertices of the leading triangle, and then followers follow a robot inside the triangle, and then design a communication topology in such a way that each follower communicates only with 3 local agents. For example, you see follower 18 updates its position based on the positions of agent 14, 10, and 17. Then, if we do that, a continuum deformation of multi-agent system can be achieved through local inter-agent communication. This is an example, and as you see, the configuration P is the initial configuration of the multi-robot systems, and a configuration Q inside the narrow channel is the final configuration. We chose the paths shown in the right top figures to guide evolution of the multi-robot systems, multi-robot system by leaders. And then in the bottom figures, you see formations of the multi-robot system at 5 sample times, and how you can see how multi-agent system deform and finally reach the desired configuration. So another task that we did is deployment a random distribution of a multi-agent system on a desired formation. For example, assume that the top left figure is the random distribution of robots on a motion field, and we desire to deploy them on a letters HT by local communication. In these 3 figures, the bottom figure shows how this random distribution of robots evolves and finally reach letters HT, but I can show this by this video, and as you see, Okay, and you see the problem of inter-agent collision among the agents is well addressed. So, in conclusion, a paradigm for continuum deformation of a multi-agent system under local communication and no inter-agent communication was developed. This paradigm has the capability of large expansion and compression when problem of inter-agent collision is well addressed. And also we showed how a random distribution of multi-agent system can be deployed on any desired formation. So I try to use math as less as I can, so my presentation was very short. Thank you so much for your attention.
Mitch and Jen like to come forward, and we'd like to open things up now for Q&A.